I was going through the point that the entropy change for an for a reversible process, if we are talking about a reversible process, for a reversible process, the entropy change would only be dependent upon this expression, and entropy generation would essentially be zero. But when we have an irreversible process, for an irreversible process, the entropy change would be dependent upon the first expression, which is del Q upon T, plus some entropy generation, which is a positive value. And this entropy generation, the value of this entropy generation, the higher the value of this entropy generation, the more irreversible your process would be, and the lesser the efficiency your system would have. Is it clear?
Yes, sir.
All right. Now moving on to a special case where you have internally reversible isothermal heat transfer process. That means constant temperature heat transfer process. In such a case, the entropy change essentially for an internally reversible process is del Q upon T. When you have isothermal process, this T is constant, which is represented by T naught. So T naught would come out of the integral, and you would essentially have summation of heats from 1 to 2 would give you the entropy change. So that means that change in entropy would be summation of heat divided by the constant temperature. That would give you the entropy change uh, for a system which is having isothermal heat transfer. This is particularly relevant to thermal energy reservoirs. If you remember, by giving it by thermal reservoirs are defined as reservoirs, they provide heat or they consume heat without change in their temperatures. So whenever a heat interaction is taking place with thermal energy reservoirs, you can express the entropy change of that reservoir with regards to the heat supplied by or the heat uh, accepted by the reservoir divided by the temperature of the reservoir. Clear enough?
Yes, sir.
All right. Now, considering the increase of entropy principle for an isolated system, what do you have in an isolated system? In an isolated system, there is no energy or mass interaction. I'll write down the change in entropy expression, which is 1 to 2 del Q upon T for an internally reversible process plus entropy generation. Is this expression clear to you?
Yes, sir.
All right. For an isolated system, would there be energy or mass transfer taking place?
No, sir.
No.
No, sir.
So if there is no energy transfer taking place, del Q would be what?
0.
That means this expression would essentially be zero.
Yes, sir.
So the entropy change for an isolated system would essentially be equal to entropy generation. Clear enough?
Yes, sir.
All right. Now, so it says the entropy change of an isolated system is equal to the entropy generation since Q is zero. And since entropy generation is never zero, the entropy generation or change in entropy would never be less than zero, which means for an isolated system, change in entropy would be equal to entropy generation. And entropy generation, you know from the previous lecture that it could either be positive or it could either be zero. So entropy generation would be greater than equal to zero. Clear enough?
Yes, sir.
All right. On to your left, there is an isolated system that has been defined. You have a system which is having heat interaction, work interaction, mass interaction, and then there is a surrounding. And above surrounding, there is a boundary that defines the boundary of isolated system in which there is no mass transfer, no heat transfer, no work transfer taking place. So if we talk about the isolated system could be splitted into the system and the surroundings, which means we can write that isolated system is a combination of system and surroundings. And in surroundings, you have all the surroundings that you have till you reach to the boundary of the isolated system. So you can say that entropy generation is equal to change in entropy of the total system, which is total isolated system, and total isolated system composes of the system itself. This is the system itself and the change in entropy of the surroundings. And this would be greater than equal to zero since entropy generation is greater than equal to zero. Clear?
Yes, sir.
All right. Now, entropy generation for a closed system with constant surrounding temperature, so that you have this system and you have surroundings which is having a constant temperature. So when you're talking about the component which is made up of system, you say that the entropy change of the system is mass multiplied by the change in entropy as the system goes from state 1 to state 2. So S2 minus S1 specific entropy multiplied by mass would give you the change in entropy of the system. And when you are talking about surroundings, which is having constant temperature, you would say that the change in entropy of the surroundings is Q surroundings, the heat transfer divided by the constant temperature, which you have seen in the last slide. And the magnitude of Q with regards to surrounding would be positive if the heat is being transferred to the surroundings. If it is coming to the surroundings, it would be positive. If the heat is moving from the surroundings to the system, the value of Q would be negative. So for an isolated system, change in entropy is equal to entropy generation. And entropy generation is basically the change in entropy of the smaller system and the change in entropy of the surroundings. Is this clear enough?
Yes, sir.
All right. Moving towards the summary of what we had covered so far. First thing, we looked into the clauses inequality, which says that cyclic integral of del q over t is less than equal to zero, where the equality sign represents reversible or internally reversible process, and the inequality sign represents an irreversible process. Then we say that the entropy change for pure substances, they can be determined from table A4, for instance, the case of water. Instead of solving this expression, you can directly find the already solved values from the table, which are given at the back of your book for the specific pure substance you're talking about. And then we looked into the fact that the entropy change for a system is closed system again is basically a combination of del Q over T plus entropy generation. And this entropy generation could either be equal to zero or it could be a positive value. It would be zero for a reversible process and positive for an irreversible process. Then you looked into the entropy generation concept for an isolated system, and you said that the entropy generation of an isolated system is equal to the change in entropy of the total system, which is made up of systems and the surrounding and gives greater than equal to zero. And for a closed system with constant surrounding temperature, you say the total change in entropy is basically the change in entropy of the system plus the change in entropy of the surroundings. This is what we have covered so far. So now some remarks about entropy. Number one, it is that a process must proceed in the direction that complies with the increase of entropy principle. That is, entropy generation is greater than equal to 0. It is 0 for a reversible process and greater than 0 for an irreversible process. A process which violates this principle is an impossible process. Secondly, it says that entropy is a non-conserved property. There is no such thing as conservation of entropy principle. Entropy is conserved during an idealized reversible process only. That means in that case, the entropy generation is 0. And it increases during all actual processes. Third thing is the performance of an engineering system is degraded by the presence of irreversibilities. And entropy generation, it is a measure of the magnitude of irreversibilities that are there in the process. Another important aspect is that change in entropy of a system. This could be a negative value. It is possible to have change in entropy to be a negative value. But entropy generation to be a negative value, this is not possible. Entropy generation, as the first point says, would either be 0 for a reversible process or it would be a value greater than 0 for an irreversible process. Moving on, some concepts about what is entropy. It is basically defined as the randomness of a system or randomness or the molecular disorder of substance is defined by entropy. That means if I move from solid to liquid to gas, the molecular disorder is increasing. And that's why the entropy of your phase is essentially increasing. So this brings us to the fact that pure crystals at a temperature T equals to 0 Kelvin would have an entropy equals to 0. It would be in an absolutely perfect manner assembled at that temperature. There would be no randomness in the system. So it says the pure crystalline substance at absolute 0 temperature is in perfect order and its entropy is essentially 0. This is also the third law of thermodynamics. And you can assess this fact that higher entropy basically means less effective system. The more disorder is there in your life or in a thermodynamic system, the less effective would it be. For instance, if you have a trolley of carrying certain weight and you are randomly applying force in the opposite directions, this would basically uh, diminish the efforts made by these four persons. इनकी एफर्ट का कुछ ज्यादा फायदा नहीं होगा. Disorganized energy would not create useful effect on how large the no matter how large the energy content is. If it is disorganized, it would not yield fruitful results. So the higher the entropy of your system, the higher the disorderness of your system, the lower or the lesser the effectiveness of your system. Just to give you an insight of what is entropy about. Let us have a look at this numerical which says that a heat source which is at 800 Kelvin, it is losing heat it is losing heat of 2000 kilojoules to a sink. Number one of the sink temperature is 500 Kelvin, the other sink temperature is 750 Kelvin. You have to determine which of the heat transfer process is more irreversible. So you have this as your system. It is losing heat to the surroundings. Your sink is your surrounding. So if you remember the expression for entropy, you say that change in entropy of your source is essentially heat released from the source divided by the temperature of the source. So this is minus 2000 kilojoules because the heat is leaving the high temperature source, which is at 800 Kelvin. So the change in entropy becomes minus 2.5 and the Change in entropy of your sink is essentially the heat added to the sink divided by the temperature of the sink. So this would be 2000 kilojoules divided by 500 Kelvin. Together, these two would make up the entropy generation. Entropy generation is essentially change in total entropy. That is the entropy change of the source plus entropy change of the sink. And this would give you the entropy generation value to be 1.5. If you look at the other part, the change in entropy of the source remains the same since the temperature and the heat that is being released the same. But for the sink, since the temperature of the sink is different, you'll have the change in entropy of sink as plus 2.7. If you find out the entropy generation in this process, which is the total change in entropy of system, it is minus 2.5 plus 2.7, which comes out to be zero point 0.2 kilojoules per Kelvin. So now out of these processes A and B, which of the process is more irreversible?
A, sir.
A, sir.
Definitely, very good. The higher the value of entropy generation, the higher would be the irreversibilities and the lower would be the efficiency. Have this concept in your mind clear. All right. Very good. Moving on, entropy change of pure
सर
substances. जी
मतलब अगर एंट्रोपी का मतलब रैंडमनेस है तो जब एंट्रोपी की वैल्यू नेगेटिव आती है तो उसका मतलब कि वो रैंडमनेस खत्म होके ऑर्डर में आ रही है चीज.
लेट्स गो बैक. अगर आप गैस में से हीट निकाल रहे हैं, gas molecules are more random, and if you are taking heat out of it, minus q, and you are adding heat to the liquid which are relatively organized, molecules are relatively organized, तो entropy liquid की क्या हो रही है, कम हो रही है. और entropy sorry, if there is heat added to liquid, if you're talking about heat being added to liquid, entropy liquid की क्या होगी,
सर
बढ़
इंक्रीज हो
जाएगी.
जाए क्योंकि पार्टिकल्स जो हैं वो मोर रैंडम हो जाएंगे उसके.
बिल्कुल. और गैस की एंट्रोपी क्या होगी,
कम हो जाएगी क्योंकि उसके एनर्जी कम होगी और वो उनकी मोशन कम हो जाएगी.
बिल्कुल बिल्कुल. तो इस केस में एंट्रोपी चेंज इन एंट्रोपी ऑफ गैस जो है वो कम होगी और लिक्विड के केस में एंट्रोपी चेंज जो है वो बढ़ जाएगी. लेकिन टुगेदर व्हेन यू टॉक इट एज अ सिस्टम, एंट्रोपी जनरेशन would either be a positive value or it would be equal to zero. Clear?
यस सर.
इंडिविजुअल कंपोनेंट्स की तो एंट्रोपी पॉजिटिव या नेगेटिव हो सकती है, लेकिन together when you see it as a whole system, entropy generation would either be zero or it would be a positive value. Clear enough?
यस सर क्लियर.
All right. All right, entropy change of pure substances. Now, when you have to determine the entropy change of pure substances, it is simple. You multiply mass with the specific entropies. And for pure substances, you normally have the tables. Just like you find out the value of enthalpy or internal energy or specific volume for pure substance such as water or the refrigerant R134A, you will do the same. If you are in the compressed liquid region, you will approximate the entropy based on two parameters, two independent intensive properties. You will approximate it as the value of saturated liquid at the given temperature. Just like you do with internal energy and enthalpy, you will do the same with entropy. Similarly, if you are in the saturated liquid vapor mixture region, you will find out using the two independent intensive properties, you will find out the entropy using the saturated liquid value, quality value, and the SFG value. Clear enough?
Yes, sir.
And in the superheated region, if you have to find out the value, you will again go to the superheated vapor tables for the respected fluent that you're talking about, whether it's pure water or whether it's uh, refrigerant 134A, you will consider the corresponding table. Moving on, we have an example which says that there is a rigid tank that contains 5 kg of refrigerant R134A initially at 20 degrees centigrade and 140 kilopascal. The refrigerant is now cooled while being stirred until the pressure drops to 100 kilopascal. Determine the entropy change of the refrigerant during the process. Now, since the mass and the volume is fixed, that means the specific volume of your system is essentially fixed. If you have to find out the entropy change for refrigerant at the initial stage, you have these two properties. 20 degrees centigrade, 140 kilopascal, find out the value of entropy. For the second state where you have 100 kilopascal, you need to have one another variable to find out the value of entropy for this state. So let's see how we can do that. You have specific volume V2 equals to V1. So at the initial condition, P1 and T1, you find out the corresponding entropy and also the specific volume. Since the specific volume at state 2 remains the same as that of state 1, you say that the second property is P2, which is 100 kilopascal given in the statement, and V2 is equals to V1. This is the second state. At 100 kilopascal, the Vf value is given and Vg value is given. If you compare the value of V1 or V2 with these two values, you would come to know that this V1 or V2 value lies between these two values. So essentially at the second state, your system is in a saturated liquid vapor mixture state. In such a case, you will use the value of V2, Vf and Vfg to find out the value of quality. And then you will use the value of quality and the saturated liquid entropy and the SFG entropy to find out the entropy at state 2. Once you have the entropies at both the states, you'll just take the difference of the two entropies and multiply it by the corresponding mass. This would give you the change in entropy of your system as your system moves from one condition to another condition. Clear enough?
Yes, sir.
All right. Then there is another example. This is now that for saturated liquid vapor mixture. It says a well-insulated rigid tank contains 3 kg of saturated liquid vapor mixture at 200 kilopascal. Initially, state 1, 3/4, 3/4 or 0.75 of the mass is in liquid phase. If 3/4 of the mass is in liquid phase, what is the value of X at state 1? Quality is defined as the mass of vapors divided by the total mass. So if mass of liquid divided by the total mass is 0.75, the quality value would be 0.25. An electric resistance heater is placed in the tank now and is kept on until all the liquid in the tank is vaporized. Here we assume by vaporizing it is meant that X is equal to 1. You have to determine the entropy change of steam during this process. In order to do so, what you'll do that the initial pressure is given to you, the quality is given to you. You will find out using these two properties the specific volume and the entropy at state 1. Again, using the SF value, the quality value and SFG value, you'll find out the entropy value at state 1. For the second state, you know that specific volume is constant since the mass and the uh, mass is constant and the container is rigid. The volume is constant, so the specific volume is constant. Uh, X2 is 1, which is saturated vapor. Using these two independent intensive properties, you will find out the entropy value, which is 6.6335 for state 2. And the rest is easy. You just have to take the difference of the two entropies and multiply it by the corresponding mass. So the entropy would come out to be 11.1 kilojoules per Kelvin. This is the entropy change as your system moves from the mixed region to the saturated vapor region. Another important thing involving property diagrams for entropy is you'll frequently encounter, with regards to entropy, the temperature entropy and the enthalpy entropy diagrams. These would be frequently encountered in different components when you're dealing with entropy. So with regards to the temperature entropy diagram, we know that ds is essentially integral of del q over T, obviously for an internally reversible process. So if you have a temperature versus entropy plot, and this is the line, the small area dA, which is the representation of a small integration process, would essentially be equal to TdS. This is TdS would essentially be equal to small heat addition for the process. Now, if you integrate the complete curve, if you integrate the complete curve, you would essentially have, if you integrate TdS from 1 to 2, if you have 1 over here and 2 over here, this would give you the complete area, and this complete area would give you the heat supplied to the system as a result, or heat transfer taking place as a result of this process. So the area under a temperature entropy curve or a process on a temperature entropy property diagram would give you the heat. On a TS diagram, the area under the process curve represents the heat transfer for an internally reversible processes. So total heat transfer during an internally reversible process is essentially represented by this expression. This is in kilojoules. If you have to express per unit mass, so you'll have small q and small s, that would give you per unit mass change. And you are talking about isothermal heat transfer, you need, can you hear me?
Yes, sir.
All right. When you're talking about uh, isothermal heat transfers, the temperature would essentially come out as a constant, and this would be T naught into delta S, which is Q internally reversible. Since you have constant temperature, you just need to have the change in entropy value to find out the heat. And for a specific case, you'll have T naught multiplied by delta S. This would give you per unit mass uh, heat transfer that is taking place. Moving on, referring to the isentropic processes, a process during which entropy remains constant. So if you see, this is the expression that we have seen so far, del Q over T internally reversible plus entropy generation. So when do you have an isentropic process? If I say I have an adiabatic process, adiabatic process, adiabatic process means what?
A heat remain constant.
That means the first part would be 0. Yes, no.
Yes, sir.
Yes, sir.
All right. And if I say I have a reversible process, entropy generation would be what?
0.
0. So in other words, if I have an adiabatic reversible process, that means the entropy generation would be what? An internally reversible adiabatic process, you will have isentropic process. That means ds, or change in entropy, would be equal to 0. Steam entering into a turbine at S1, there is no irreversibilities within the system, that is internally reversible. There is no heat transfer taking place, that means your system is adiabatic. In such a case, the entropy at the final state would be same as the entropy at the initial state. Clear enough? Is
Yes,
it
sir.
clear? All right. Now, how do you represent the isentropic process on a temperature entropy diagram? It's an isentropic process is represented by a straight vertical line. S2 is equal to S1. This is an isentropic process. And you see, since it's a line, there is no area under the line. That means it is representing a process which is adiabatic. Q is 0. Clear enough? So this is how you represent isentropic process on a TS diagram. Is this clear to you?
Yes, sir.
All right. Remember, isentropic process is the ideal process for some of the steady flow devices such as turbines or compressors. So this process, the isentropic process, is used as a reference or the best possible process for devices like turbines, nozzles, and compressors. If I specifically refer to turbine, what is the purpose of turbine? Workout?
Yes.
All right. So if a turbine is working isentropically, if a turbine is working isentropically, the workout would be maximum or minimum?
Maximum.
Sorry,
Maximum.
The maximum.
it would be the maximum possible workout. But if I say that instead of turbine, I have a compressor which requires work input. For an isentropic process, the work in would be maximum or minimum. G,
Minimum.
it would be
Maximum.
minimum possible work required input. When you want the work output, it's your need to have the work output from a turbine. So an ideal process, which is an isentropic process, it would give you the maximum work out from the turbine. But if you're talking about a compressor which requires work input, ये compressor में आपको काम करना पड़ता है. You have to provide work input. So in an ideal case, which is an isentropic case, you will have to give minimum work input in order to run the compressor. Clear enough?
Yes, sir.
All right. Moving into an example of an adiabatic turbine. It says that steam enters an adiabatic turbine, adiabatic Q is 0, at 5 megapascal 450 degree centigrade. So two conditions are given to you. With these two conditions given to you, you can find enthalpy, you can find internal energy, entropy, specific volume, all you can find out with these two conditions given to you. And it leaves at a pressure of 1.4 megapascal. Determine the work out of the turbine per unit mass of steam if the process is reversible. So adiabatic reversible process entropy is what? It is an isentropic process. That means at this condition S1 would be the same as S2. So you have two properties also at the exit. Is it clear? Is it clear or not?
Yes, sir.
So if you look at the steam turbine, you know energy principal E in is equals to E out. En is coming in terms of enthalpy, H1. E out, which is going out, is H2, which is again the enthalpy, plus the work out. So this is the energy coming in, this is the energy going out. H1 you can find out using these two conditions. H2 you can find out from these two conditions. This would give you the work out. So if you look at the process, the first process is 500 megapascal and the temperature is given to you as 450 degrees centigrade. You're representing the temperature entropy plot. This is P1, constant pressure line. For P2, which is 1.4 megapascal, you have a constant entropy process from 1 to 2. This is isentropic expansion. So E dot in equals to E dot out, M dot H1 is equals to W dot out is equal to M dot H2, W dot out is equals to M dot H1 minus H2. You know H1 and S1 from these two conditions, H2 from these two conditions, and your work out is essentially H1 minus H2. This would give you the work out of your turbine. This is the maximum possible work out that you can get out of turbine. Actual work would always be less than this work for these conditions when you're talking about 5 megapascal and 1.4 megapascal from 450 degrees centigrade to 1.4 megapascal line. Is this clear to you?